But what we will do now is I'll say thank you very much, Arash, and now I'll try and connect to our next, while I fumble around with my browsers, our next guest speaker, who is Marzieh. So Marzieh is a postdoctoral research fellow at the CIC. Prior to joining the CIC, she worked as a researcher at Data 61 CSIRO and a lecturer at New South Wales in Melbourne. She has a broad set of interests in machine learning, abnormality detection, Bayesian learning and analysis, iterative data fusion, and privacy in IoT.
Well, I'm going to give a presentation about my recent work that I have done in Data 61 CSIRO, and we have already published a paper from that, and we have extended this research, which is going to be published as a journal paper. The title of the project is Motion Spice, Vibration Energy Harvesting Sensor Can Track Train Passengers Using Machine Learning Techniques. I'm going to give you an overview about the project and then the motivation for us, that why we are using this technique to highlight the privacy leakage of the data. Then I'm going to give a brief explanation about vibration energy harvesting, which are the sensors which will be available in our wearables and smartphones soon, and also the methodology that we are using, followed by the data collection and evaluation of the preliminary results. As you know, the public transportation becomes very popular recently, and there is an increase in the number of people who are traveling on public transportation. In most of the countries, we have more than 30% of the people who use public transportation. For example, in Australia, about 35% of the residents are using it, 36% in Australia, in the state, 30% in Scotland, and about 44% in Europe. Apparently, the train or metro line networks they are mostly underground, where there is no GPS and wireless network. So we have some issue to communicate, let's say, or to have access to this infrastructure. So we are going to present a study that shows how we can identify the train route or train trip of a user using the smart device like wearables or smartphone or the devices which are equipped with a sensor, especially motion sensor. So even though you don't have access to wireless network or GPS, it is possible that a malware application to be installed in your mobile devices and have access to this motion data, and then this data can be analyzed and used later to infer the trip that you have taken on a train. And this information, as you know, can be later used to violate the privacy of the people, or we can find some some private information from the user side. For example, we can see if we know that a user is traveling every day, at a specific time from this station, from station A to station B, then probably we can find out that his home or her home is in this region and the place that she's working is in that area. So it can make some issue for the privacy of the user. Currently, most of the smart devices are equipped with embedded sensors such as accelerometer, GPS, magnetometers, and different sensors. And from the state of the art, we know that it is possible to infer some contextual information from this sensory data. For example, we can infer the location of the user. We can find out what's the activity, some information about health, and etc. This information can violate the privacy of the people. So, especially if we are going to use this sensory data to track the user, we can get, as I told earlier, we can get some specific, private information from the users. Generally, tracking can be done by using or monitoring the GPS of a user, or some accelerometer measurements, and even the device battery profile. So it's possible that we get the location of the people from this information. But now we are going to highlight the usage of motion data that can be extracted from motion sensor, that I'm going to give you a brief explanation about it in the next slide. So if we have like a passenger who is traveling in a train, on a train, it's based on the motion of the train. We have a specific pattern of the data. So we can use this motion data, which shows a specific, which shows actually the movement of the train over the railway. And if this motion data has been accessed by an attacker, it is possible that they can, find your location on the railway system. Transportation system. And they can use VH-based train route identification technique that I'm going to present it here. What's the motivation for this research? I have shown a graph here that presents the accelerometer measurements of from a smartphone. And this smartphone was carried by a user while she was traveling on train. As you can see, there is a sequence of data, like I call them segments. There are 11 segments here, which has been separated by green color. And for each segment, which represent a station interval, we have a specific pattern of the data. And these data are shown, or let's say is reflected in the accelerometer data in acceleration. So we can see that a train ride from accelerometer measurements could be represented as a sequence of the patterns of data. And each of these patterns or segments are separated by stop times. So for example, at the beginning of segment 10 and 11, I have shown them in the red color. You can see that for this period of time, the train has been stationary, which makes sense because it was, stopped to open the door. To let the passengers enter the train or leave the train. So this is the main motivation. If we can have this data in acceleration or in accelerometer measurements that shows the data in a sequence of pattern, it is possible that we infer which stations the user is traveling on. We are not going to use accelerometer. We use vibration energy harvesting sensor, which is actually a self-powered sensor. The level of the energy which it is producing is in the level of microwatts. So for now, it is not that much high that we can say we can use it as a battery. But the point is that it is self-powered. It doesn't need any, battery to work. And the main idea for this sensor is that it harvests power from any vibration that could be from ambient or human activity. So this vibration can be represented as motion data, and we have shown that there are papers in the literature that show that there are some rich contextual information in these motion data, that we can use them for activity recognition, for step counts, for transportation mode detection, and even user authentication. So we are motivated to use these data, these signals, to see if it's possible to find out that which station interval the user is traveling on. So we consider VEH, or vibration energy harvesting, as a motion sensor. So we have converted the accelerometer measurements to power. There is a model which is called spring mass model, which you can use them to convert the accelerometer measurements to VEH measurement. And the results, I mean the outcome of the model is VEH, or let's say total power in microwatt, which is a scalar value. As you can see here, I have a figure that shows the measured power, or let's say the calculated power from accelerometer measurements that I had in the previous slide. So you can see that even the VEH data which we have here is shown as a sequence of like pattern, and it might be used, that was the motivation, it might be useful to extract some information from, to recognize each segment individually and use them to infer the trip of the passenger. So the methodology that we are using is that we have a VH trace like the one that we have here, and it has been measured by the sensor in the smartphone or the wearable devices. So the input of the system is a VH trace. Then we are going to use a component which is called segment extraction. It is actually a threshold-based algorithm which is going to extract each segment from the others. For example, here it is going to to have this 11 segments separated from each other. And what we are going to use here is a threshold-based algorithm, which actually try to have like a temporal window which is moving over the signal, and then try to detect the stop time and recognize each segment. It is very similar to the technique which is used for speech recognition. Then in the second component that we call it segment recognition, we use two techniques, dynamic time warping or classification techniques, to model each segment separately. The output of the segment recognition will be like different segments which with a model. And then for a specific trip, we have a set of the segments here as the output of the segment recognition. Then there is another component which is called trip inferring, and it uses some reference segments from the map and from the training files to infer the user's trip. I will explain it later to show why we are using trip inferring components. To evaluate our preliminary data, we have collected data from 36 trips. So each trip, the number of total stations which are represented are 40 stations, that all of them has been collected from Sydney metropolitan area. And it's from, you can see that in the map in the right side, that for example, one line is from central area to the north of Sydney, we call it which is called North Shore line, and the other one is west line from Central to Stratfield. So for each line, we have several 60 station intervals. All the data has been collected from Samsung Galaxy S3 with sampling frequency of 100 Hz. We later extended this data set, and also we have collected the data from specific hardware which is equipped with a sensor, and the result is very similar to what we have from these preliminary results. For the first component, which is segment extraction, as I mentioned, we have used threshold-based technique which is widely used in speech recognition. So there is a temporal window which is moving from the beginning of the signal, and whenever that we have the value of this temporal window lower than let's say a specific threshold, then we can consider it that it is in a stop times. So we will have it like as a unique segment. So we will extract it as a segment. To use this approach, we have find out that 80% of the segments that we have extracted they have been extracted correctly with like let's say 10-second error. That means that because we have this moving temporal window, it is possible that we miss a little bit from the beginning or the end or both sides of the segment. So the summation of the error, it could be maximum 10 seconds. That's what we set for our data set. And we can extract 80% of the segments with a good accuracy. Then we use these segments for classification and also for dynamic time warping to do the pattern recognition. Unfortunately, the results for dynamic time warping was much lower than classification. So I have just reported the results for the classification technique here. For the classification, we have used 45 time and frequency domain features. And then we have used correlation-based feature selection to select the best features for the proposed data. And then we have tested the data for different classifier, which are ensemble, logistic, supported vector machine, decision tree, and naive Bayes. And the accuracy that you can see here is something, the best accuracy can be achieved from ensemble classifier, which is 61%. As you can see, this accuracy is not high. It's very close to like, let's say 50. And the point is that this is the accuracy that we can identify a specific segment, one individual segment. So that's the reason that it motivates us to use the trip inferring component, which is the third component. In this component, we are going to use a sequential property for VEH or even accelerometer data, the motion data for our results. The reason is that we know that the trip over a railway, it has a sequential property. For example, we have a specific segments or let's say specific stations which are in sequence. So if we have the map of the, let's say, the network, the transportation network, we can use it to identify that a trip which has, let's say, the length of 3 segments or 3 stations, it can be actually it cannot be any combination of the 3 segments out of the stations. It is just a specific set of trips which contains 3 segments. So we are using this sequential property of the trip for VH data here. And as you can see, when we use this sequential property, we can increase the accuracy of the trip inferring. So this is the result which is shown for the trip inferring. As you can see, for one segment, it is 61% from ensemble classifier, about 60%. But when we have 2 trips, by using this sequential property, we can improve it. And like in 5 stations, we can have the accuracy of 91%. And it converges actually to 100% for the trip inferring for trip inferring from 8 stations. For the conclusion, we believe that these results highlight the privacy leakage of the data from motion sensors, which could be like VEH data, because they have rich contextual information. It is possible that to infer the route and the train trip of the passenger from this data. Also, the experimental data has been used to evaluate our proposed method, and we have collected the data from Sydney Transportation Network. And the results show that we can infer the trip of 5 stations with the accuracy of 91%. The results that we have achieved here is lower than accelerometer data, but we know that using VH data, it is more cost effective comparing to accelerometer based data, because when you are going to use accelerometer, you need to use magnetometer and gyroscope with it to do some coordination, alignment, which is widely used for localization. So we need to have 3 sensors. It's not just going to work with accelerometer. So we need actually 3 sensors to achieve the higher accuracy. Moreover, accelerometer data has 3 dimensions which can be measured in X, Y, and Z. Like it's a 3 dimension data, and it is the same for magnetometer and gyroscope data. So we are going to use actually 9 sets of data for inferring the data from MEMS, from, let's say, accelerometer, magnetometer, and gyroscope. But for VH model, we are just going to use the power, which is 1 dimension data, and we need to have the features for this 1 dimension data. So in terms of the algorithm and even computation, it is more efficient as well. Thank you.
So thank you very much indeed for that. We really appreciate the time you've taken to speak with us today. That was absolutely fantastic. So I'm just going to try and see if anybody wants to ask any questions. I think that your presentation was particularly concise. Nobody? Okay, well that's absolutely fine. Is there anything else, Marzieh, that you wanted to comment or reflect on with your research?
Oh, no, that's fine. I just wanted to say that we have actually extended this work because we wanted to do more study to see how the results will be for a more complex network, and also um, uh, for a device which has been equipped with a vibration energy harvesting sensor. So we have analyzed all these data and the results already, and hopefully you will have these results published soon.
That's absolutely fantastic. I think, like Arash, you're doing some absolutely phenomenal research, and I think that there's a huge opportunity for us with our IoT work that we're doing, along with everybody else, to be able to try and collaborate with you sometime very soon. That would be great. So I want to thank you both for joining us today for a fantastic event, and we hope to see you and hear from you very, very soon. So thank you very much for joining us, and have a great day.